Okay, so you've seen some basic trig identities. You've seen at least a couple of examples of how you use the identities to restructure algebraic equations so that you can solve them. Another thing you can do with identities is you can use the basic ones to prove more complicated ones. So here's a question. Is this an identity? In other words, is the left-hand side always equal to the right-hand side? Well, one thing you could do is try and plug in some values of theta, and if you find a value of theta where the two sides are different, you know it can't be an identity. But if you do plug in a value of theta and both sides come out to be the same, how do you really know it works for all values of theta? Maybe you just chose one that was special that just happened to work. So what you can do is you can use algebra and you can use the other identities you already know to try and rewrite one side so that it looks the same as the other. And we've done this before when we were demonstrating other identities. So this is where it's helpful to have kind of a list of all the identities that you know so that you can kind of look at it and see what could I do to restructure what I have. So I hope you recognize from an earlier video this 1 minus sine squared. This is another form of the Pythagorean identity. And what I'm seeing is if I could rewrite this in terms of cosine, then I'd be able to cancel. So let's do that. If I subtract sine squared from both sides of this equation, I have cosine squared equals 1 minus sine squared. Here I've got 1 minus sine squared, so let's just substitute in cosine squared. So now I've got sine, cosine, and then in the denominator, I've got cosine squared, 1 over cotangent. Cool. So now I've got the cosine in the numerator is divided by one of the cosines in the denominator. So now I've just got sine over cosine, which is the same thing as tangent. And here I've got tangent equals 1 over cotangent. If I were going to take the reciprocal of both sides, or if I was going to multiply by cotangent and then divide by tangent, I would end up with cotangent on the left is 1 over tangent on the right. And that's like the definition of cotangent. Or if you wanted to, you could write this all in terms of sine and cosine. So let's turn tangent back into sine over cosine. Let's have 1 over cotangent be 1 over cosine over sine. And now on the right-hand side, we can multiply by the reciprocal, giving us sine over cosine. And now we see the two sides are the same, and we've demonstrated the identity. So that's the exercise, and it's a bit of a puzzle. It's not always going to be obvious what the right path is. Sometimes there's more than one thing that you might be able to try, and maybe the thing you try is going to work out, or maybe it's going to make everything worse, and then you got to back up and try a different route. So this is sort of very authentic to what actual algebraic problem solving feels like a lot of the time. Let's do one more, and then I think you'll be ready for the problem set. All right, let's try this one. Tangent x plus cotangent x is secant x times cosecant x. So here, it's not obvious if any identities really apply. So a nice trick that you can use is rewrite everything in terms of sine and cosine and then see what you can do. So here we go. All right, so far so good. It doesn't look particularly promising, does it? But one thing I'm thinking is here I've got two different fractions. What if we combine them under the same denominator? Because here I'm noticing, when these are multiplied, this is the same as just 1 divided by cosine times sine. Here I see the denominator here is cosine, the denominator here is sine. If I was going to combine them under a common denominator, the denominator would be sine times cosine, which is what we've got on the right here. So that actually feels kind of promising. Let's do it. So this one I'll multiply by sine over sine. This one I'll multiply by cosine over cosine. Okay, so you can see I sort of snuck it in there. So here I've got sine times sine, so that's sine squared in the numerator, plus cosine times cosine, so that's cosine squared in the numerator. In the denominator, they're common now, so sine theta, cosine theta. Aha, this is starting to look good. So denominators are the same. What do we notice about these numerators? Pythagorean identity. sine squared plus cosine squared equals 1. Right from that earlier video. So, you know, we're done. Sine theta cosine theta equals 1 over sine theta cosine theta. And then, you know, smiley face. Okay, let's actually do like one more. All right. So what could we do with this one? So I'm noticing some tangent squareds, and I'm noticing a cosine squared. I'm thinking, could we apply a Pythagorean identity? Let's just remember what they are. So sine plus cosine, I'm going to leave off the thetas, okay? Equals 1. It doesn't really seem like... Okay, so I could do this. I could get cosine squared minus 1 by subtracting 1 and subtracting sine squared. So cosine squared minus 1 is opposite sine squared. So I could substitute in opposite sine squared here. It's not really obvious that that's going to help me, but that's one thing I could do. Could I get a tangent squared plus 1? Is that possible? So let's remember how to turn this into an identity involving tangents. If I divide by cosine squared, then sine squared over cosine squared will be tangent squared. This is plus 1. And then this is 1 over, what did I divide by? Oh, yeah. So 1 over cosine squared would be secant squared. Okay, so that's nice. I'm noticing that this entire thing could be replaced with secant squared. And now I'm putting that together with what I saw just a second ago. So if this whole thing is secant squared, and remember this whole thing was opposite sine squared, then let's think about what happens when we multiply those together. Secant squared is 1 over cosine squared. I'm multiplying that by opposite sine squared. So put that all together, and we've got opposite sine squared over cosine squared is opposite tangent squared. So that seems to have worked. Is that the only thing we could have done? Probably not. I bet it's going to work out if we just like multiply this whole thing out and see what we get. So let's try it that way. If I multiply this whole thing out, I've got, it's going to be a little ugly. So tan x times cosine squared x minus tan squared x here plus cosine squared x minus 1 equals opposite tan squared x. Okay, so what's going to happen now? Tan squared is, let's rewrite in terms of sine and cosine. So that's sine over cosine squared times cosine squared. I'm freely exchanging x's and thetas here. Sorry, my hand is so used to writing thetas. Let theta equal x. Okay, now I'm safe to do whatever I want to do. Okay, but notice, so those are going to cancel. So when I'm multiplying tan squared times cosine squared, those cancel, and I have just sine squared. Awesome. Okay, so minus tan squared theta plus cosine squared theta minus 1. So maybe I do still need something. Well, I guess I could do this. I guess I could add tan squared theta to both sides. So that becomes nothing. This becomes 0. So now I just have sine squared plus cosine squared minus 1. See where it's going? Sine squared plus cosine squared we know is 1, because that's Pythagorean identity. 1 minus 1 is 0, so we've got 0 equals 0. And we've demonstrated the identity. So you can see that sort of if you keep the faith, you know, we could probably come up with 2 or 3 other ways of solving this if we really wanted to. But that's the exercise. The exercise is sort of seeing what could you do and algebraically massaging it until it does what you want it to do. All right, good luck.